This simulation demonstrates a server encountering 50,000 concurrent requests for the first time. The physical vibration and eventual failure represent the gap between a controlled local environment and the sudden impact of high concurrency demand. A functional localhost environment masks the physical limitations of your infrastructure. Your machine provides a dedicated database and zero latency, creating an environment that cannot be replicated at the scale of a production cluster. The first point of failure is often invisible. Missing or unvalidated environment variables deploy silently, only triggering runtime crashes hours or days later when a specific code path finally attempts to execute a missing key. Next comes the diagnostic collapse. Without centralized request tracing, a single user action bouncing across a distributed microservice network becomes a web of isolated logs, making it nearly impossible to locate the origin of a failure. Then, the primary bottleneck hits. Heavy background tasks, like processing a CSV file or generating a report, monopolize the single-threaded Node.js event loop, freezing the application and locking out every other user waiting for a response. Maintaining availability under these conditions requires 4 specific defense mechanisms. First, boot time validation. Next, pervasive observability. Then, distributed caching. And finally, asynchronous queues. Operating at scale requires isolating business logic within a hardened perimeter designed to contain infrastructure failures before they impact the end user. The lifecycle of an application begins at the bootstrap phase. In a modern pipeline, the exact same codebase will be deployed across diverse targets, moving from local environments to isolated staging servers, and eventually into multi-region production clusters. Each of these environments requires distinct database credentials and API keys. Relying on implicit unchecked process.env variables means your application will successfully boot even if a critical key is missing, guaranteeing a failure the moment a user requests data. Notice raw.env variables entering the NestJS boot sequence. They must pass a strict validation gate enforced by a class validator schema. Valid strings pass through, binding the application to port 3000. If a critical variable is missing, the entire boot sequence instantly aborts. This fail-fast strategy prevents misconfigured code from ever entering the deployment pool. The deployment pipeline will register the aborted boot as a failed health check and immediately halt the rollout. Forcing an application to abort at boot is safer than allowing a misconfigured application to receive traffic. A dead application takes 0 requests, while a misconfigured one can silently corrupt incoming data. Once the application is running safely, we have to monitor how it handles traffic. Standard console.log statements are insufficient. Stringing text across a terminal provides 0 actionable data at scale. Instead, the system requires structured JSON logging, where every log entry can be automatically indexed, queried, and tied to a centralized request trace. We achieve this by integrating Winston as our external logging engine, providing standardized JSON outputs. This timeline maps the NestJS request lifecycle. A request moves sequentially from middleware to guards to interceptors, through pipes, and finally to the controller. Global middleware intercepts the request, attaching a unique trace ID. That specific trace ID is tethered to the request as it navigates through the controller and executes logic inside the service layer. If a query fails, the error routes back out to a dedicated exception filter block at the edge. The exception filter acts as a safety net. It captures the raw internal stack trace and binds it to the initial trace ID before writing it to the Winston logs. Simultaneously, the exception filter strips sensitive database details from the payload, ensuring the external client only receives a sanitized HTTP 500 error response. DevOps engineers aggregate these JSON logs using external dashboards. By searching a single trace ID, they pull up the exact lifecycle of the failing request without needing access to the production server. Binding logs strictly to the edges of the request lifecycle ensures every internal microservice error is traceable back to its specific user origin. When a massive traffic spike hits an unbuffered database, it slams the disk with force, maximizing CPU until the database cluster completely locks up. To protect the database, we use externalized state management. We implement distributed caching by pairing the NestJS cache module with a high-speed in-memory Redis data store. As shown in this diagram, the caching logic is positioned directly in front of the controller inside an interceptor block. When a unique request arrives, it passes through the interceptor, querying the database and caching a copy in Redis. Seconds later, when 10,000 identical requests arrive, they hit the interceptor block first. The interceptor reads the active Redis cache and instantly bounces the data back to the clients, bypassing the controller and database. Interceptors can achieve this because they utilize RxJS observables. These streams allow the application to short-circuit the execution context and return a response without waiting for the internal layers to mount. When you combine this caching layer with rate limiting enforced inside the guard blocks, you effectively neutralize aggressive API abuse and denial of service attempts. Resolvers catching requests before they reach the controller layer minimizes the CPU and memory footprint of every redundant query, preserving core compute resources for unique operations. Node.js operates on a single-threaded event loop. It can handle tens of thousands of concurrent connections, but it processes computations one at a time. Synchronous, CPU-heavy tasks like generating PDF reports or dispatching bulk emails will lock that thread, increasing latency for every other user attempting to fetch data. To solve this, the architecture requires an asynchronous pivot, routing heavy processing requirements out of the API thread. This illustrates BullMQ integrated with Redis. The API controller receives a complex payload, but instead of routing down to an internal service, it pushes it laterally into a queue. The controller immediately returns a 202 accepted response, freeing the HTTP thread. The API controller has fulfilled its only responsibility, validating the payload, acknowledging the request, and persisting the job to the data store. In the background, a separate worker process, running on a different server, pulls the job from the Redis queue and executes the heavy compute task without touching the API thread. Because the worker is separated, the job is persistent. Even if the main API goes offline, the worker will continue processing the queue, and if the worker crashes, data remains safe in Redis. If a third-party email provider rejects a dispatch, the queue provides automatic exponential retry logic without impacting user-facing API performance. Offloading heavy workloads into asynchronous queues allows an API to remain responsive to user interactions, regardless of the volume of background processing occurring in the worker cluster. We have taken a brittle, monolithic CRUD application and wrapped it in the structural defenses required for a distributed, fault-tolerant enterprise system. The config module sits at the base, guarding the boot phase by ensuring no application starts without its exact environment contract. This macro view shows the completed architecture. Winston captures telemetry directly at the edges. Redis intersectors buffer the center, while BullMQ workers operate asynchronously on the side. Inside this perimeter, clean business logic flows smoothly through the service layer. This separation ensures business logic remains decoupled from infrastructure concerns, allowing teams to scale global constraints without modifying core service code. With the application code hardened for production traffic, the final step is containerizing this cluster with Docker and deploying it to a scalable AWS environment.
Enhance your coding skills with us. Don't forget to subscribe to Code 5 Food for the latest updates and tutorials.